Okay, continuing with chapter 4, we're going to continue with crankshafts. And we talked about the angle of the crankshaft on a diesel engine is longer. The throw is going to be longer because we have a longer stroke. So the purpose of a crankshaft, convert the linear motion into rotational motion. The crankshaft journal needs to be hard so that it doesn't wear out. So we're going to talk about inductive hardening, which is the most common way of doing that. The journal, again, is wrapped with a coil of wires. High amperage is traveled through it. As it travels around, it hardens it and induces electricity goes into it, and it makes it really hard. So they're going to make it a hard surface. They have a longer throw. Because we have a longer throw, this length is longer. The crankshaft on a diesel engine has to be stronger, has more torsional torque. So as that engine has a harder thrust, it also has more torsional torque. That torsional torque is going to cause the crank to break easier, so they need to be stronger and they need to be more durable. So there's a lot of torque that develops, and so it's a different design, a slightly different design, very similar, but more attention is paid to how strong they are. You can see they have lots of different pieces to it. Balancing holes. We looked earlier, we've seen the holes that are drilled in the crankshaft for balancing. Those are normal. We have a flange to attach something to the end, and there's lots of ways we can attach a flywheel or some kind of business end of the engine. Connecting rod journals. We have our main bearing journals. We have our fillet radius, and they make a big deal out of the fillet radius. Anytime, and we know that from grinding our rotary blades, if you have a 90 degrees, the crack always starts right there on that corner. So we try not to have any 90 degrees. So each one of these journals here has a rounded fillet that's in there. So they don't grind it flat, they grind it with a radius that spreads the tension out and prevents it from cracking right there. There's oil passages that are drilled from the main bearings to the crank journals. And so we're going to feed each one of these main bearings with oil. It'll come out of the main bearing and then go to our connecting rods. And that's how they will be oiled. So there's an oil passage drilled through there. You would think that's going to make it weak, but the hole's pretty small and it's drilled through the middle, so it's not really affecting it. But each one of them should have some way of lubrication. Here's our main bearings. Main bearings oil supply holes. You'll notice that the bearing itself has a groove down the middle. The groove down the middle is so that oil comes in, oil will travel around. It's going to go into the hole of the main bearing. From there, it's going to travel out to our connecting rod. So this bearing is not going to be a perfectly smooth bearing. You will find on the connecting rod, a lot of times they'll be smooth. Well, on the main bearings, because we're going to make the oil travel around and it has to be feeding that hole all the time, we have a grooved bearing in here. So upper main bearings. Looking at this, I have a lot of students that'll say, hey, there's something wrong. My bearing, the connecting rod journal has got really hot. And you can see because it's all blue here. That bluing took place when they did the inductive hardening. That's actually normal. It should look like that. That tells you that they hardened that surface. So they're going to wrap that wire around there, they heat it up and cool it down, and that's how it's inductive hardening. So again, you can see here we don't see a square edge, we see rounded corners, and then we see an oil hole to let the oil go in and then come out in our connecting rod. So this is my main bearing, this is my connecting rod journal. Machining, a lot of diesel engines, because they do that inductive hardening, it's really hard on the outside. A lot of them, they don't allow you to turn them. So we're used to turning cranks and using oversized bearings. Some diesel engines will allow that and some diesel engines will not. So before you go sending it off and making a lot of decisions, you want to see, can I actually turn this crank? There are people that will take a crank and they will actually flame spray metal back on and then turn it back down. So it's still back to the original diameter, but they flame spray it and then they have to harden it. And so it's specialty shops, not something you will ever do in your shop. So they have to have the perfect kind of equipment to do such things. So machining a crankshaft is possible on some. I know that when we looked at the Mitsubishi, that they had undersized bearings, oversized bearings, because you're going to be turning the crank. The bearing has to be oversized to actually fit, and they have oversized bearings for this Mitsubishi. So in this case, it is allowed, but not all engines will do that. Nitriding is a process where they heat the crankshaft in the main bearing journals, and then they introduce cyanide salt or liquid CN3, and then slowly cool it. That absorbs that, I think it's like a nitrogen stuff, absorbs into the metal and makes it super hard. So that's another way of heat treating the crankshaft.
But that only goes so deep into the metal.
It's only going to go so deep. So if you turn it, you would probably go through it. So it's going to be very limited.
To resurface it.
Yep. And if you resurface it, you'd have to try to do this process again. Otherwise, it would be soft and hard. So certain cranks, that's why you would look, do they allow it? If this surfacing only goes a certain, thin layer, then I wouldn't be able to turn the crank.
Right. Because that hard surface only goes down a few thousand, so
You grind it off, you're done. So fillet rating, we talked about that. We want to make sure there's no sharp edges. Any reputable person that's turning cranks or polishing cranks would know not to take that out. Crankshaft lubrication, we already showed you some of those, and we're going to talk about it again on this engine a little bit. But crankshaft has to be lubricated. There's got to be some passageways in there. They need to be clean. When you put your bearings in, you want to make sure that those holes are not covered up. And so if you put the bearings in wrong, sometimes you can cover up the hole and you would starve it for oil, and it's going to have a problem. So always be kind of aware, do my oil holes line up? When you put cam bearings in, there'll be a round bearing with a hole. You got to get them lined up and then tap it in and make sure that the oil passageways line up. Otherwise, you just block them all off. So in all cases, crankshaft, camshafts, all bearings, make sure that you don't cover up the holes. All crankshafts, when they're running, end up with some kind of harmonic vibration that's in there. And we talked about balancing the crank, balancing things. There are parts on the crankshaft to take out the vibration, and then we also have dampeners. So we're going to talk about some dampeners. And if you don't have a dampener or the dampener goes bad, it puts this vibration through and it will fatigue and break your crankshaft. This is that fillet weld. When they machine it, it's in there. We have an oil passageway that goes through. Oh, is there any questions about that? Vibration dampeners. There are various kinds of vibration dampeners and methods that we're going to use to absorb the vibration. One of them is elastomer, one is viscous, and then combination dampeners. And so we'll see some pictures of them. Balance shafts, we already talked about it, where they use this is yeah. So this is like a secondary, it looks like another camshaft or crankshaft that have balance, and they'll be chain or gear driven. And so they're going down when the piston's traveling up, and they're going up when the piston's traveling down. So they're just opposites. We see this a lot in the gas world with single cylinder engines, because we'll have a big counterweight going the opposite, or counter rotating flyweights to counteract that vibration dampener. Usually they're gear driven, so they don't ever get off. So if you have that in your machine, it's critical that they're timed. There's a process, you put them in, make sure they're all timed. Otherwise, you'll make it worse if you're like throwing the counterweight and the piston in the same direction. That engine will it'll bust everything up. It'll be a bad situation. So secondary countershafts is not all that uncommon. We see that a lot in four-cylinder engines. We'll see some counter-rotating balancing shafts. So different ones. If we don't have them, or if they're bad, we lose the crank. Here's an elastomer one, and the elastomer is rubber. And this inner part is bolted on to the crankshaft, it's solid. and then there's a layer of rubber, and then there's an outer big heavy piece of metal. And the outer piece is completely, controlled by the rubber. And as the engine is speeding up and slowing down with all those events that we talked about, that outer piece is just flexing and absorbing that torsional shock. If this starts to get old, they'll start to see cracking in it. That thing will actually rip. If it rips and disappears, the whole piece will just come off. So the only thing holding it on there is the glue of that rubber. It's glued in place. And if that rips, that counter thing just, full pulley comes off. A lot of times this will have pulley things on it. We're actually running our water pump and radiator fan, that kind of stuff. So there's a lot of tension on it on big engines to be running other things. They go bad. If I'm looking my engine over, if I'm overhauling my engine, I want to look very closely at this, and it would be worth its money to replace that if you think there's any chance that it goes bad. Because if it goes bad, it wipes out your crank. So it's expensive compared to this. But this one's on a rubber. What happens when I take my puller and I stick my puller on the outside of that, push on my crankshaft and pull this thing off? You're just going to rip this thing right off the rubber and you're going to leave the inner one. So you never ever pull by the outside. Just like we don't pull on the outside of flywheels on small engines, we don't pull on the outside of one of these. We're going to push here, and there should be some bolt holes in here that we can screw bolts in, and you're going to pull on the inner hub, push on the crankshaft. Don't put pry bars on there and pry on it. Don't do any of that stuff. So, very important piece of rubber. This is a viscous dampener, and I don't know that I've ever had one of these, but they say this is filled full of silicone, and there's just resistance in there. So as it's spinning around, that viscous is actually absorbing that tension by running in that.
It's almost like a torque converter.
It's kind of like a torque converter, but it's running in kind of a
Much thicker
thick silicone stuff that doesn't really gel up. And so the resistance of that is absorbing that tension, that vibration that's taking place. I haven't seen any of these in the stuff we have out here, but I haven't seen everything. And then the counter rotating balance shafts. Here I have my crankshaft. I have a balance shaft on each side with just a chain tensioner. So this one's using a chain. And I'm trying to run those opposites of whatever the direction of the piston. Piston's traveling up, the weights are going to be on the bottom. The piston's traveling down, the weights are going to start going towards the top. So I'm just trying to make them go. And you'll notice that these two are coming towards each other, and then as they rotate, they're going to be going out, and this one's going out. So they're going out and going up. So they balance each other, and they're balanced in the piston. So it's really important that you don't just stick them in there. Almost everyone I've ever seen has always been gear driven. So you line up all the gears, stick it in. But chain would be the same thing. You just got to make sure you time them right. So vibration dampeners, whatever kind they are, don't drop them. Don't pull on the outside. Make sure you follow the book, pull from the inside, and then you're going to inspect them pretty carefully and make sure that they don't look like they're damaged. And if they look damaged, you're going to want to replace them. Inspecting them, check for timing marks. So they show on that one picture that there was lines on it, and it kind of lets you know that the rubber has slipped. If the marks aren't lining up, you've actually rotated. Once you've rotated on that rubber, it's going to come apart. So you're going to want to replace it then. Check for springs. Some of them actually have springs. They're going to show in the next picture. They show tensioning stuff on the clutch, the engine clutch area. And those will be spring, taking some of that tension out with springs. So if they're springs, make sure that they're tight, they're not loose. You shake them around. And other signs of slippage that's damaging. If it's the viscous kind, if there's silicone starting to ooze out, all those kind of things. Dual mass flywheels. So another place that can absorb some of that tension is in the flywheel and the clutch area. Two separate sections can be disassembled in inspection. So they're going to show a picture of this. So it's like two pieces. I've never seen this kind either. There's two pieces wedged together. They actually kind of tension on each other. So I've never seen one. So I don't have much information. It's like a clutch, but when you see the picture, it's not like a clutch. So I'm a little confused how they work. So power is transmitted to the flywheel clutch mounting surface through a series of springs located around the circumference of the inner plate. So it's kind of what you would do with a clutch. But the picture they're showing is not really a clutch.
The force of the rotation is spread out.
Yeah, so I jump ahead. Here's the picture of it. And so you've got your flywheel, which is this inner piece here, and then they have this plate. And you can see where the tiny marks are lining up over here, but not over here. So somewhere between these two plates, they're showing, or supposedly have some kind of springs. I haven't seen one of these, so I don't know. So we'll look at some of the clutch stuff. This one here is a flex plate. So if you have a torque converter, or if you're not using some kind of clutch, if it's a hydrostat operated machine, a lot of times they'll have a flex plate. A flex plate is just a thin plate that gives me a place to put a ring gear. There's not a lot of mass there, so I have something else that creates mass that helps carry through in the rotation. Whereas having a flywheel, a big heavy flywheel, this flywheel adds mass and helps smooth out some of those vibrations that you have. So part of the vibrations can be absorbed by the physical mass of the flywheel, because the flywheel is not going to just speed up and slow down, speed up and slow down. It's so big, it helps carry through and smooth out those power events that are taking place, and it evens it out. So a big heavy flywheel will help. The problem with a big heavy flywheel is it slows down. I stump on an accelerator and I got to speed up that flywheel. My efficiency, my snappiness is gone. Whereas a flex plate doesn't take much to speed it up. Here they're showing clutches, different kinds of clutches. This is a dual mass clutch. Primary mass, secondary mass. So these would be like clutches gear transmission that I'm shifting gears. And within the clutch itself, we have springs within the clutch. So this is a common thing. Most clutch discs have an inner set of springs or rubber or some kind of tension. So when you let the clutch out or you hit a load, the pressure, the torque between the transmission and the engine, whether it's coming from the engine or coming from the transmission, there's some kind of spring, either rubber or metal springs, that absorb that tension between the two. And when you pull this thing apart, you want to make sure that these springs shouldn't just flop around. If you shake it and they're rattling around, there's something wrong. They're worn or their spring tension's gone, something's wrong. So this is another form of dampening some of that stuff. So that's it. So I want to look at this. This is an engine block for a Mitsubishi, and a couple of things I want to point out. One is going to be the cooling system. The cooling system only goes to the bottom of the cylinder. So you want to unplug that and roll over here. So if I roll this up, you guys want to climb over here? When I lift this block up, you can see the bottom of my cylinders, and there's a kind of a flat area here. On this side is where the camshaft goes. On this side over here, you don't see anything. That's actually the bottom end of the cooling system. If I rotate it to the side, here are my soft plugs. That area is right here. This is the bottom of my cooling system. That's the bottom of the piston. And at the very lowest point is a plug. And this plug would be if I want to change my cooling system and I want to drain my antifreeze out, I put water in it, I'm flushing it, whatever I'm doing, you want to drain the water out of the block. Just draining it out of the radiator leaves this whole block still full of liquid. So it's important somewhere at the bottom of the cylinder should be a plug of some sort that allows me to drain my block all the way. And it's a pretty common thing for students to drain the radiator and maybe the hose, but they don't drain the block. And so there's got to be a plug someplace. And it's going to be above the oil line. So this cavity, this line that you see in the cavity here is oil, and above that is going to be my cooling system. And typically it's going to be right below the soft plugs. The soft plugs we talked about are for sand castings. It allows us to build it. And if we're overhauling it, we have a lot of junk in there, we can pull them out and gives us access to help clean out rust and that kind of stuff. So I helped a student take a V8 out, and his cooling passageways up to the little over halfway up his soft plugs was solid debris. So we took the soft plugs out and you couldn't see anything behind. We took a screwdriver and took it out, and then we started cleaning it out, and we chipped and chipped and chipped and chipped and gouged and chipped, and over half of his cylinder was garbage, rust, and he probably had holes in the radiator, so they put bars leak. Bars leak is just like junk. And so they had half the passageway was full. We took his engine apart. He had lots of signs of overheating. Well, when you look at his cooling passage, you're like, yeah, no, I can see that one. I mean, you took half the capacity away, and then all that trash that was in there was contaminating and taking up all the stuff that's in my cooling material itself. So antifreeze itself has got, anti-freezing protection, and then it has boiling protection, and then it actually has stuff to protect it from rusting. So there's an additive package that we talked about in the first stroke class. That additive package is going to get ruined by the debris that's in the system. So if it gets debris in there, you see rust in your antifreeze, you need to run a good cleaner, clean it really well, and you would want to be draining this all the way to here. And I would keep washing and washing and washing and add water, flush it, add water, run it for a while, dump it out, add water again, dump it out, until I start flushing out clean water. And then it would go back, flush it completely, drain it, and then go back to my mixture, typically a 50-50 mixture. Never run water, straight water. I mean, you can run water to do a cleaning, but don't run it long term. And that's what happened in these liners that we looked at earlier. These liners are from running straight water on it. And in not very many hours, wiped out the engine.
So that must have anti-cavitation additives in it too?
Yes. So because the antifreeze helps keep the water from turning into bubbles, it keeps it from cavitating. So yes. So the second thing we got in this block is oil. Somehow we need to direct oil around this block. So this particular engine, we'll start here. This is where the oil pickup. So this has a tube that comes out. There's a little screen on it. This is my oil pickup. Oil is going to come in here. Comes out this hole. This is the cover for it. So this is the hole that matches up with this one. So the suction oil is coming in here, comes over, and this is my oil pump. So it's coming in to this side, comes through the oil pump. It's going to discharge out to this hole that's here. There's supposed to be another one of these here, like a little spacer in there, and that lines up with the top one. So it goes from here into the block. If I rotate the block around, if I come out of the block, I'm coming down, you can see this high spot that's here, comes down here, and it's going to come out in my oil filter. I always want the oil to go through the outside of the filter to the inside. All filters are supposed to go that way. So I'm going to go from the outside through the filter into the inside. The inside lines up with these ridge that you see coming along here, and this is going to be my filtered high pressure oil, whatever pressure is supposed to be, and I'm going to go through my block now. And so if each one of these little screw holes that you see here is going to line up with a main bearing. So we have holes in our main bearing. So here's the inside of that ridge. The ridge comes across the middle, so You take that screw out, that's how they actually drill the hole. Drill comes in, we drill down. Oil is going to come into the main bearing. It's going to go through that groove that we looked at. And part of the oil is going to go out the other side of the main bearing and go down to my camshaft. So I'm feeding my camshaft. I'm also going into the crankshaft. So I have the hole in the crankshaft. That's drilled diagonally up to my connecting rod bearings. And I'm going to, oil goes to the connecting rod, oil goes to my camshaft. So there's the oil there. One more important piece that it does. So you notice we had two of these passages with. So one of them was feeding my oil filter. The second one is in that same line, the same line that we fed our main bearings with. There's another one coming out here. It's going back into this cover. So the question is, well, where does it go from there? It's the lower one of these two. So the lower one goes in. If we rotate this thing, the lower one is inside this cavity. So you can see there's a ridge. I can follow it. There's a screw over here. We're going to drill this thing over to this passageway. And go down. And then we have an object here with a big, huge plug on it. When I rotate it around, there's a somewhat large hole, and if you can zoom in it, you can see there's something in there. This is my pressure relief. So I always want my oil system, all oil systems should have some kind of high pressure relief. If you get too much pressure, we want it to dump back into the reservoir. If it gets too high, it squirts out this hole, kind of comes into this cavity. This cavity is lining up with this piece, and we just drain back into the oil pan. So it allows the gear to pick it up and fling it around, that kind of stuff, and it drains back into my oil pan, suck it back up, repeat the process. What would create too much oil pressure in an oil system?
Passages maybe be clogged.
So I got a lot of debris in there, and I start lodging stuff in there. I mean, I don't know. Let's say for chance someone actually left a paper towel in the oil pump, okay? That would never happen, right? Unless you were a student. They left it in there, that got in the system, plugged up the oil filter. If it got chewed up enough, it got through the oil pump, didn't plug up the passageways, I could plug up the filter, and the filter could build up some back pressure. And if it builds up back pressure from the oil filter, what's going to happen?
The filter's gonna bypass.
It's going to blow a seal, because this restriction is after the oil filter. So if the oil filter gets too dirty, this particular system has nothing to protect it. It's going to have to blow a seal, which is kind of odd. Normally you want the safety relief to be before it, unless there's a bypass in the filter. And you can buy two different kinds of oil filters. You can buy bypass filters and non-bypass filters. If you buy the wrong one and it doesn't have a bypass filter and it starts to plug up, it's going to blow a seal. And the only seal there is this little O-ring, which is going to be challenging to do. So it's going to cause damage. So you want to make sure you always buy the right filter. So this filter should have a bypass. You start it up, the engine oil is really cold, the filter is really dirty, you haven't been changing your oil. It's going to open up, it's going to dump dirty oil through all those passageways. If the system itself for some reason has too much oil pressure, then it's going to come here and dump. And one of the ways that's going to have too much oil pressure is you're going to overhaul your engine. I overhaul my engine, what did I do? I machine it, I put new bearings in it, the bearings are really tight, the crankshaft is, at its maximum diameter, the tolerances are, I'm like right at the minimum of everything, right? So I've tightened up all my tolerances, and this pump is going to be a gear type pump. It's putting out X amount of oil all the time, no matter what. So if I tighten all my tolerances up, after it reaches each one of these bearings, it just leaks past the bearing and dumps back into the oil pan. If I tighten up the tolerances, my ability to dump somewhere is gone. So earlier we had a question that said, What creates high oil pressure? Well, high oil pressure would be resistance. Resistance to flow is going to create pressure. We know that from our hydraulics class. So how do we get pressure in the system? We have resistance. So resistance to flow creates pressure. The gear pump just creates flow. It's designed to put X amount of pressure or X amount of flow no matter what. I step on the accelerator and run the RPMs up, it puts out a greater flow. If I have no place for it to go, it creates resistance. Resistance creates pressure. My tolerances don't get bigger as my RPMs goes up, right? So if my tolerances don't get any bigger and my RPMs go up and my flow went up, what's my pressure going to do? It's going to go up. So you get in your car and you start it up, you're idling, it's like barely got oil pressure, you step on the accelerator, oil pressure comes up. Why? Because my pump is pumping greater flow. My resistance in all my bearings remains the same. Same resistance, greater flow, or not really the same resistance, it's the same tolerance, I should say. Increase in flow, I'm going to have greater oil pressure.
So what causes oil pressure to drop once your engine gets warm?
So as oil gets hot, the viscosity goes down.
It thins out and it flows better. It makes all the oil and better.
So if it flows, the thinner the oil gets, the easier it is to flow past these tolerances. So as we flow past those tolerances, my oil pressure drops because resistance went down. Resistance goes down, the same volume is going to go, the pressure is going to go down. So how do I compensate? I put a multi-viscosity that has a higher high end. So 1550. And so 50, when it gets hot, means it's got the viscosity of a 50 weight oil, really thick oil. So if I put a 1550 in there and my engine gets hot, it's going to have better oil pressure. I read my owner's manual because I just got this vehicle and I don't realize that it's in bad shape. And it says put in, 530 weight. So you change the oil, you put 530 weight in, and it had 1550 because the guy's like, man, this engine's bad. Let's make it look good by putting thick oil in. You change it to this thin oil, you go out there on the highway, it gets hot, and you're like, oil light starts coming on. Why? Because 30 weight is a lot thinner than 50 weight, and thinner oil goes past the tolerances, oil pressure drops. So these little stories about people, I want to sell it, let's put thick oil in some ways. Well, it's compensating for its ability to go past those tolerances. So it's a cruel way of screwing somebody else. So this one, because I want at a brand new engine, I don't want to put a smaller pump in for a new engine, and then as my engine wears out, put bigger pumps in. And it's a gear pump, so the pump doesn't vary. So with a brand new overhauled engine, we put a pressure relief valve that says when you get to a certain pressure, you rev it up instead of just keep going up, you get up to 50 oil pressure, 50 psi. I want to relieve it. So this, it's on this side. Oh, this side. This oil pressure relief is going to relieve the oil at a preset amount. So I'm not going to go any higher than a certain amount.
So when you just have a brand new engine broken, you have really, really high oil pressure. Is that why there's a screw head on it, a ball head, so that you can relieve the pressure?
This particular one, no. I think if you opened it, you'd probably have to change a washer or something in there. So typically you don't adjust it. I mean, some of them might be adjustable. If they did, it will tell you within your book how to do it. So there's going to be a screw within there, or you're going to change washers and change spring tension. So, but it should be the same tension whether it's a brand new engine or a wore out engine. All that does is set the upper limit. If my engine wears out, my tolerances start wearing out. If I go in there and I shim that tighter, I didn't actually raise my oil pressure. All I did was try to mess with the high end, but if my oil pump is not putting enough oil out, because first of all, it's now wore out, and my tolerances are wore out, so it has more places to go, that's still not going to give me more flow. And it's more flow with the same resistance that's going to give me oil pressure. So you'd be better off.
Forget about
You'd be better off pulling out the pump and replacing the pump and trying to increase the tolerance of the pump, or changing some bearings to shrink the tolerances. But screwing with this thing here, all that does is, okay, now I have to overhaul. So I overhaul my engine. I forget that I screwed around with this high-end thing, and I start it up. It's got cold oil. It's a spring, winter day, and I'm like, cool, this thing sounds so great, and I romp on it, and I bring up this volume with these tight tolerances, and I tighten that thing down to where it won't bypass, and my oil pressure goes whomp, hegs, and I'm going to start blowing things. So I'm going to start doing damage. So you don't want to mess with it. You really don't want to mess with it. If you have to mess with it, you don't understand the system, for one. And two, you have some other problem. So messing with that, there's no reason that you'd mess with it. So it's only setting the upper limit. And I rarely, other than tight tolerances and cold oil, it's the only time I ever hit, and in max RPM, that's when I'm going to hit maximum. And that's the only time it comes into play, is at that point. So understanding...
It's actually a good thing to watch your oil pressure gauge go up and down as you're driving. It's a good thing.
And you know, going up, you haven't reached the upper limit. And going down is because my tolerances are... I'm just not getting it. And really, I just need oil pressure. There's a minimum amount, because the minimum, if I start getting too low, it's going to go to the biggest cavities and dump out, and as soon as it dumps out, we're not going to get to the critical areas.
And if the pump was high enough flow, then that it was always dumping over the relief, then the relief would actually compensate for the viscosity of the oil changes when the engine warms up, and so you wouldn't even notice the pressure difference on the gauge. Possibly.
I'd have to think about that one. So, top of my block here, I've got all these little passageways. One of these passageways has got to come up to another item that we haven't talked about, which is my valve train that's at the top. Somehow I have to lubricate my valve train. So this particular block, this hole that's over here in the corner, if you rotate it, you'll see there's a kind of a hump here, and it's going down to my camshaft. And so this cam bearing that's down here, oil is going to come from my main bearing, goes through the main bearing, comes up to this cam bearing. From the cam bearing, it's going to go up into my rocker arm. So as my oil pressure starts to drop and I'm at the minimum oil pressure, what's the first thing to lose oil? Lubrication.
Camshaft.
Not the camshaft, the rocker arm.
Highest.
The highest point. First of all, it's got to get to the highest point, and it has to feed everything else before it can get here. So I got to feed my cam, or my crankshaft, then I got to feed my camshaft, and then I got to get up here and go down my rocker arm. So this rocker arm down here is the last thing to get oil pressure when I start it in the morning. And if I lose oil pressure because of whatever, it's the first thing to lose oil.
Yeah, because you need pressure to get it up there.
If I had a turbocharger, we would tap into there and it would go up and we would feed the turbocharger, and it's always fed out the top end. And so when you shut a car off with a turbocharger, the first thing to lose oil pressure is a turbo, and the last thing to get oil pressure when you start it up is the turbo. So you start it up, you stick it on the floor, it's a couple of seconds before oil even gets to the turbocharger, and it's already screaming because as soon as you turned it over, it started to spin. And when you have this thing revved up and you shut the key off at full throttle or even half throttle, that turbo is spinning really fast, and you shut the key off, what's the first thing to lose oil pressure? The turbo. And does it stop as soon as you shot the engine? No, you hear it. It is slow and down. The whole time it's doing that, it's doing it without any oil lubrication. And so it's critical that you idle all the way down, let it cool down some, and then shut it off. So if it's an emergency, you want to get the RPMs down and then shut it off. Because even getting the throttle down, it'll actually use that air to slow itself down. It'll get it down before you shut it off. And at least you have oil pressure while it's coming down. Okay? So two critical things. This side over here does have some soft plugs, so there's a little bit of cooling trying to go in between where my lifters are coming out and my push rods. There's a place on the end down here, so we have a little bit of area behind that we can open up and kind of clean out. And then in the front is going to be my water pump, so I can access and clean some areas down in here. So box, got to do a whole bunch of stuff. Another object that's hanging out the side over here is my fuel pump. So you notice I didn't tell you any place where oil passages came up to my fuel pump. Fuel pumps are lubricated by
Diesel fuel.
the diesel fuel itself. And so this particular one, this is not the right one, but it's a very similar looking one. This is kind of what the fuel pump looks like. And so everything within this block is lubricated by the fuel itself. Outside, they got these little roller bearings, and you have a little camshaft that runs here. That camshaft and these roller bearings are fed and lubricated by the engine oil, but there's no oil passageway to get here. There's no little injector thing squirting oil up on there.
Splash lubrication.
So this situation is splash lubrication. So if I rotate the block and I rotate it up, can you see down in there? You should actually see all the way down into the bottom of the cavity. As the crankshaft is spinning around, it's going to fling oil up. So it's kind of like the slinger system on our little Briggs engines. It's a slinger system. It's slinging oil up there, splashes, and just like a Briggs, when you turn an engine over at 1,000 RPMs, you know, you open the cache and look in there, and you're going to be poof, black. I mean, it's going to spray a lot of oil around. And so the crankshaft is hitting this oil, and it's flinging it up there, and we're going to have plenty of lubrication to do that. So,
And the splashing too of the cylinder, of the piston arms and stuff will also lubricate as well. But, you know, they keep things cooled down in there.
so oil will be splashing. We got oil splashing up, running down in our pistons and cooling. Oil's running down, so I'm cooling the whole bottom end. Everything below this plug, because that's the plug, everything below that plug, the bottom of the piston, connecting rod, everything below that is cooled by the oil. So anything down there has to be clean. If I have a bunch of oil caked on this thing, this is sitting inside of a box and the box is all full of mud and whatever, it's not cooling. That oil pan has oil on it and grease on it, it's not cooling. If you got a skid plate, the skid plate's full of mud, it's not cooling. You've taken away the oil's natural ability to radiate heat out the cover of the pan itself, the oil pan. So that has to be clean. You got to keep that cleaned out. And it's really common to find skid plates in the oil pan. I mean, everything, drop the oil pan or the skid plate off and it's got the perfect form of everything. And people don't understand how important that is. And they can't understand why their oil keeps going bad so quick. Okay? So, cooling, oil, pistons and all that stuff. This block, the reason I have this block is we machined 10 thousandths off the top of this block. 10 thousandths, the piston hit the head. 10 thousandths was too much. So, we took 10 thousandths off because there was a leak between the cylinder and the cooling passage, actually here. So we had some pitting between it like we have in this other Toro over here. And that pitting, to get the pitting out, we had to take 10 thousandths off to get through the pitting. Well, 10 thousandths on a diesel was too much.
So did you have to take 10 thousandths off the top of the injector pump? When did that change the difference between the pistons and the cam?
Yep. And then we would have had to go through and change the shims. And there's a whole bunch of shims. So there's a packet of shims that you buy, and you would go through a process. We would have had to re-time the fuel pump to make it work. So it was complicated, but we had pitting. So we thought, how do you solve pitting? We took it off, we put the thing together, everything was turning over, we put the head on, clunk, clunk, uh-oh. You can't buy a head gasket that's thicker, you can't buy a shim to make it thicker to compensate for the 10,000. You buy a block. So that's things you got to be aware of and be careful about. Okay, any other questions? That's chapter 4.